This is our Team 4272 FRC Electrical fall series. Um, so I wanted to start off with introducing ourselves, myself and Don. Um, um, I've been around the team for I'm saying 7-ish years. Um, my my oldest daughter started with the team. Uh, this will be my 7th season, and I was just kind of hanging around and being interested the first couple of years before becoming a legit mentor, registered and all of that. Notice the PE on my name. I am a licensed professional engineer in Indiana. I can talk about that if anybody's interested. Essentially, it's a state credential the same way a doctor or a nurse or an accountant would get a state license. It's a little rare in electrical engineering, but it's very, very common in civil engineering. That's credentialing mainly for working on projects where public safety is a concern. So, buildings, roads, and bridges, things like that is utmost public safety. Electrical engineering is quite a bit less, unless you get into electric power. The utility grid has a lot of licensed professional engineers, but things like consumer products and programming the next big app or doing some database work for an organization doesn't really have that emphasis. One of the key things that I bring to FRC Electrical on our robots is that I started my career with a company that built wiring systems for Caterpillar, and I bring a lot of that experience to our robots, and we'll talk about that a little bit later. And I'm currently with Matrix Technologies. Matrix Technologies is has been a sponsor of our team for many years now. And Don, do you want to talk a little bit about yourself?
Okay. I'm Don Cook. I'm an electrical engineer. I also have a BS in electrical engineering. I got mine from the University of Illinois. I started, 8 seasons ago with a team in Michigan. We're still in the process of moving from Michigan, but I'm here in Lafayette, and I'm a senior digital hardware design engineer. That's what my title is. And I primarily do work on board level design. I do board design, and I also do embedded logic. And I work for a company called Radian Research, and I'd really like to get them to be a sponsor, but with COVID, I don't really want to invite my CEO to get sick. So anyway, I am not a licensed PE, but it's something that in my area of expertise, nobody really does that. It's just a hoop that we don't really have to jump through. So that's kind of good in that regard.
Yeah, I don't mind saying it. To get it is an 8-hour test, and it is without a doubt the hardest thing I've ever done.
So I can get hired without it, so I haven't bothered.
Absolutely.
The thing that I can bring to the team is if there's something that we want to do that where we can't just buy it off the shelf. I can help design things that will take care of functions that we need for our robot. Last year, we made a little miniature power distribution panel, and that was mainly to help manage our wiring so that we didn't have a huge excuse me, rat's nest of wires going back from the central part to where we needed to provide power to sensors. So, but I can help with that. And if anybody is interested in electronics, you know, down to the transistors and diodes and all that stuff, and want to play around with that, you can get a hold of me, and we can do stuff that's not necessarily team related if you're interested in learning about electronics. So,
Yeah, something else I wanted to throw out here was I've had the opportunity to there's a PCC class, I believe it's called, that's um, used to require some job shadowing. I think that's kind of relaxed with COVID, but I've done job shadowing with team members. I've arranged job shadowing with other people for some students before. So when those sorts of things come up, um, um, keep us in mind. We can help with that. I know a lot of people in a lot of different companies, and I may be able to make some connections for you. So enough about us. One of the things that is concerning to me is that a lot of students feel like the electrical system of the robot is just too daunting. It's too complicated, and I'm here today to just say no, it's not. It really isn't. There's this the the resolution of this graphic got a little potato on me, but there's better versions out there. Um, there's not a lot to it. I know a lot of students who build their own PCs, um, do car stereo systems. If you're looking at match speakers to amplifiers and things like that, the FRC control system is no more complicated than any of those things. If you're picking components for a PC and and doing your research to make sure that the components are all going to work together properly. Um, uh, FRC is way easier because we've got lists of qualified components. You choose your parts from those lists, and pretty good chance they're going to work together because they've been kind of pre-selected. And then it's just a matter of getting them connected together correctly. I don't know, any other thoughts. I put home theater system in here. And then I got to thinking home automation devices. Some of the Alexa connected light switches and lamps and some of those things. Although that's pretty simple. The home theater components, and I was really thinking more about video monitors and Blu-ray and sound systems and all of that. So Q&A, is there? No, not what I'm after. Let's see. All right. So, what about the engineering? And yeah, everything in electrical engineering is pretty well based on two ideas. One is Ohm's law and the other is Watt's law. Those are the foundational ideas of electrical engineering. And you know so there's a lot of questions around the electrical design that goes into a robot, and and we can and as mentors, we're here to help with that. So want to maintain that open channel for questions, and later on, we're going to talk about a little bit with wire sizing. Well, clearly a larger wire can carry more power than a smaller wire. That just seems logical, right? Well, that comes down to the resistance of a larger wire being smaller than the resistance of a smaller wire. It has to do with, physically how much material there is in parallel in a wire. Why does that matter? Well, the relationship of Ohm's law that resistance causes current to happen or causes a voltage drop when current is applied. And Watt's law then indicates that how much power is dissipated by that resistance. So a smaller resistance is a lesser power drop. One of the things that you'll notice when we get into competition with the robot is that we can pretty well sap out the battery in a match. Often we'll be browning out on the robot by the end of a match if we've got a very power intensive robot, and we've done some of those in the past. We've built some very fast robots, and not only fast, but also powerful, able to push some other robots around. And we've found occasions where at the end of the match we just don't have enough in the battery to do the end game climb. And so that's so managing that efficiency, managing losses. So why not just put big wire on everything? Well, it's heavier. So there's a design balance there to be sought between efficiency and weight. The difference between volts and current is something that we thought to put on here. You can think of voltage as being potential. I always like the water analogy to electricity, that voltage is the amount of vertical drop, the potential energy.
The analogy is a waterfall.
Yeah. The electricity always flows from high potential to low. And so you have that vertical delta is analogous to your voltage, but then the flow of the water is the current.
One thing before we move on, in the equations that are shown, the I stands for current. Those are algebraic equations. And we don't generally need anything more complicated than algebra for what we do. So it's not complicated.
Yep. What does AHR mean? That's amp hours. That's capacity on a battery. The regulation battery for FRC robots is I believe 17 amp hours. And like I said, we've had occasions where we can totally use that up in a 2.5-minute match. One of the key, how does an encoder work? I don't want to sketch it out right now, but there's it's essentially two signals, and based on one leading and the other lagging, you can tell what direction a shaft is turning, and then by the frequency, you can tell how fast it's turning. What is a circuit? Well, I think everyone learns in a science class somewhere along the line that the electricity has to flow in a circuit. That means that there has to be a closed loop all the way from the source to the load and back to the source. The reason that's important is because you're looking at a flow of electrons through that circuit, and you can't create or destroy them, and they don't like to be too far from home. So you'll have electrons travel out of a battery through the load of the circuit and back to the battery, where they're bare minimum being replaced by others, but essentially the same electrons are making the full circuit, the full path. And without that, you have an infinite resistance somewhere in your circuit and no current flows. But one of the things that I wanted to focus on here is that it turns out you can do an awful lot without knowing any of this. A lot of what makes a successful electrical system on a robot is the workmanship, and doing a quality job. Many times when we have an electrical failure on the field, especially ones that leave the robot dead on the field, more often than not, those are not design issues. Those are workmanship issues. Almost exclusively workmanship. Because if you've got a design issue, it wouldn't have worked in the first place most of the time. So the next thing we're up against is next thing I've got on the agenda here is to talk a little bit about design choices. And a big idea there is whether things are going to be centralized or distributed. Pretty well anything that we only have one of is going to be a centralized design just by its nature. So power distribution, our battery will connect to the power distribution, and then from that power distribution, you'll have power lines go out to all the devices on the robot. and robot communication. We've got one point of communication back to the field and to the driver's station. The Robo Rio is the main controller. We've only got one, and by FRC rules, can only have one. And so those things are central by nature. The motors, on the other hand, will have motors all over the robot, and then motor controllers. Well, do you want to pull those in close to the power distribution center, or do you want to push them out to be closer to the motors? This has been changing over the last few years, especially with the new brushless motor controllers. The original brushed motors that were exclusively used in FRC when I started just 6 or 7 years ago. You had 2 leads for your motor and no feedback from the motor itself, and so those things were we had a tendency to pull those in close to the power distribution center. In some cases, we'd mount them right onto the back of it, and for a compact or compact as we could get it, electronics board all in one place. But the new brushless motors that are in a lot of ways superior to those older motors that have been incorporated into FRC robots in the past, probably 3 years, maybe 4.
It hasn't been that long.
It hasn't been that long at all. Starting with Neos, and I'm trying to think, the new one is a Falcon.
I don't know, but
okay.
The advantage of the brushless motors over the brushed ones is that they're smaller and they're more efficient. And those are 2 wonderful things for our robot.
Yeah, the Neo motors, the old Sim motors are about 4 pounds a piece, and we've built robots that had 6 of them on the drivetrain, where the new Neo motors are every bit as powerful, possibly a little bit more powerful.
I think so.
And they are less than half the weight. I believe the full size Neo motor is only a pound and a half, versus like 3 or 4 pounds for the Sim motors. And weight is one of those things that we always run out of at the end of the robot, at the end of the build. It always seems like we're tight on weight. So that makes when you're talking having 6 of these on a drivetrain, being able to save that's 12 to 18 pounds that you're talking about saving, which makes a huge difference. Considerations in the design of your robot is that it may indeed be easier to find small spaces for those controllers distributed out around the robot, rather than one bigger space to put them all in the same spot. We've the students I've worked with on electrical over the last several years, and I have put a lot of effort into trying to streamline down the space requirements, the footprint of the electronics and control for the robots. And I think we've done pretty well. We've come a long way. But now the counterpoint to spreading these parts all over the robot, troubleshooting can be a little bit more difficult. A lot of these devices have little indicator LEDs on them to tell you that like a motor controller would have a blink code to tell you that it's got a problem. And if all of those are in one place, you can scan right in your field of vision and see that they're all good and happy. But if they're scattered all over the robot, especially if they're pointed down at the ground or something on the underside of a drivetrain space or something, it can be tough to spot those when you're looking for a problem. One of the things that can happen is you'll break a wire on a communication line, and typically what happens then is that everything downstream of that break in the communication network doesn't work, and so finding that one, and you don't typically run everything at once, so you might know that your shooter's not working, but not know that your feeder is not working either, because you're not running them both at the same time. So that just one of those things to kind of keep in mind. So the next thing I've got here is power versus signal wiring. Do we have, I'm missing the chat. Is there anything going on?
General comments, but I don't think we have any questions. If we do, they'll chime in again, I think.
Okay, very well. Let's see. All right, I'll quit playing then. Okay, so I got to thinking about power versus signal wiring, because that seems to be one way to split things up. Most of the devices on the robot are going to have both. Some devices are going to be power only. Some will be signal only. Signal only devices would be things like sensors. Some power only devices. I don't know. I suppose like your voltage regulator module would be power only, which it takes a 12-volt in from the battery, and it produces a regulated 12-volt output and a 5-volt output for various things on the robot. And so that would be an example of a power only device. I'm going to talk later about there's a they're talking about a new power distribution center. The power distribution center would be another power only device that it's kind of like a fuse panel or the breaker panel in your house. that it brings in the high power um, from the battery, and it offers protection and distribution of that power to all the different devices on the robot. Um, they're talking about a control system upgrade for it was going to be for 2022, but it might be 2023 now because of the pandemic and maybe just natural delays in getting it rolled out too. But one of the things that they mentioned there was that the new power distribution module may have some switchable outputs that will be software controllable. And
So even though that's a power only device, it does have some control leads on it. We haven't gotten to this yet, but it's called a CAN bus. It's a control bus, and it has green and yellow wires.
That's
So
right.
even our existing power distribution panel, you can read things from it, and it does, even though 95% of the wires are all red and black because they're power, there's a little pair of green and yellows that allow us to talk to it. So that's a key for when you see that, that means that that's the control bus. That's a signal, rather than power.
That's right. That's right. I overlooked that. Yeah. Um, because that over that control network, we're able to read I believe voltages as well as currents through each of the channels. Although the voltage should be consistent throughout. It may just be the bus voltage, but individual channel currents, which is a neat troubleshooting tool. If you think you've got a motor going bad and it's in parallel with another motor, you can compare that and say, okay, well, there's these two motors that are running together, but one is using significantly more current than the other one. There's some interesting power, some interesting troubleshooting that can be done with that information. Another thing that I wanted to throw out there was that a lot of the devices have both power and signal. So in particular, the new motor controllers, the new motors typically have integrated encoders on them. They have and they have the capability to wire limit switches into them. So, like if you're doing a lift and want to have a bottom limit switch to indicate to the motor controller that you can't go beyond this point. Those things can often wire into the motor controller themselves, and not all the way back to the Robo Rio. And we've done a little bit with that. Would like to see us do more of that in the future. But yeah, a lot of that signal to wiring is distributed in that regard, that it's central to the motor controller and not and doesn't have to come all the way back to the main controller. Power wiring, if you're just looking at the robot cold and don't know what you're looking at, power wiring is typically red and black. It's typically bigger sizes of wire. I'm talking about star topology here. That is that there is a central point and individual runs of wire go out from that PD board out to each of the devices on the robot. Um, each motor, for instance, each device, um, with a couple of minor exceptions that we've never dealt with, by the rules, have to be separate, um, separate runs from the PD board. There are some rules that I think are a little antiquated now, and will especially be antiquated with the next with the next revision of the PD board, that allow, I think, two motors off of the same channel, if you have adequate circuit protection installed. But it's never been something that we've needed to deal with. Um, um, but as a general rule, everything is straight line run from the power distribution board out to the devices. The connectors that we use for power wiring, is going to be the Anderson power pole connectors. Those are a square kind of Lego block kind of connector, that we started using probably, um, um, we started using those on Steamworks, and changed them out on the robot in the pits at Worlds, with that robot. Prior to that, we were using a pre-insulated disconnect terminal, and had some problems with those because of some crimp quality issues, that we were having terminals pull off of wires at a pretty alarming rate. Another connector that we use on power wiring is the ferrules. So it's essentially a cleaned up, stripped end of a wire. A ferrule is a tube that a metal tube that slips over the stripped end of the wire and crimps to a square-ish shape, and we'll go into cage clamp style connectors on the PD board in particular. This is where we use a lot of that. But most of the prime FRC components will use ferrule connectors for talking about the PCM, we'll use those. The VRM module will use those, and the Robo Rio and the power distribution module, because they're designed for that cage clamp style connection. And then of course lugs, that we use on the battery cables. And that pretty well sums up power wiring, what you'll see there. Signal wiring, on the other hand, there are a couple of different standards that are used in signal wiring. And most everything is a standard of some sort. Red, white, black is used for analog circuits and for PWM circuits. Green, yellow, we mentioned earlier, is for CAN bus. About anything that is not just simple red and black is going to be signal wiring. Ethernet is a 4-pair cable that is orange, brown, green, and blue, and
yes,
each of those pairs has a white with color stripe that pairs with it.
It's standard, and you have to get it right, and you just do it the way that everybody else does it, and it works out.
Yep. Um, encoder wiring can be about anything. I think I've seen purple wires in there and all sorts of things. A lot of that is going to be proprietary. Whatever comes from the vendor, whatever comes from the manufacturer is what you get.
The rules are that generally you should be using red, black, and white for power, ground, and signal, green and yellow for CAN, and then if you have any other um, piece of electronics or hardware that has attached wires, whatever color wire the manufacturer puts on it is cool with first. So you can end up with sensors that have got black, brown, and blue wires. That's okay because that's just how they come.
Yeah. This is one of the reasons I love having Don around, is because Don has actually served as a robot inspector among the many things that he brings to the table for us.
One thing I wanted to mention before we go on, one thing that's weird about electrical is that the bigger the wire, the smaller the gauge. So the power wires have got relatively small gauge numbers, and the signal wires have got larger gauge numbers. So
Yeah, yeah, that's a really good point. The battery lugs are typically going to be 4 or 6 gauge wire, which is quite large. Um, the but what we run for our motor controllers is typically going to be 12 gauge, which is smaller, despite the the number being larger. And then some of the signal wiring that we do is going to be 20, 22, 24 gauge, possibly even smaller.
most of it's 22, but you can use larger gauge wire if you want to make sure that it's more robust. We've got a robot status light that we put on our robot, and in the past, we've used 18 gauge wire to connect that just because we had the wires get pinched and broken off. So you can use larger, smaller gauge wire if you want to.
Yeah. Um, yeah, I one of the things that I can add on there is that the CAN bus wires that we use are typically 20 gauge.
They're 22.
Are they 22? Okay.
Yep.
The green yellow twisted pair. But when I was working on projects for Caterpillar, they were running CAN bus in 14 gauge wire. And the reason for that was that the smaller gauge wire was getting damaged when they would do a high pressure washdown of an engine, and so they weren't really interested in running anything smaller than like 18 gauge wire. But in that particular case, they were running a green yellow twist pair for CAN bus that in 14 gauge.
That's interesting.
It was it was electrons don't care particularly. The network works fine, but they had other design considerations on their mind, particularly the robustness. And that being said, signal wiring is typically smaller wire because you're not carrying any current. You're just carrying a signal. You're carrying data. And power wiring can be, or I'm sorry, signal wiring can be point to point. like an Ethernet cable or a USB. CAN bus is a trunk line where you'll have a trunk line from end to end, and you'll tap off of that at the different devices. CAN bus is a linear network. And other things will be a star topology where you'll have like if we were to have some sensors that wired back to the Robo Rio, those would be just like the power wiring from the PD board would be straight line runs from the hub out to the device. Connectors that you'd see on those if you're looking at the robot. We've adopted a Molex connector that Don had used with his team up in Michigan, and is clearly superior to the stock connectors for signal things on the Robo Rio. And I say clearly superior in that these Molex connectors have a latch on them that physically holds the connector together, so that you have to pinch to release it. Where the standard connectors on the Robo Rio are just kind of push on, and they're a friction fit. Some teams have done some 3D printed things, brackets and such to hold those in place. But we've in recent years, and this is one of the impacts that Don brought with him with his experience on another team, was to utilize an MXP board that will screw down to the Robo Rio, use these superior connectors, and get us a more robust design that we can run into other robots. We can bounce the robot off the walls of the field and bounce over obstacles on the field and things like that, and not risk losing connection to devices on the robot. Signal wiring also uses a lot of ferrules. A lot of these things are having to wire into boards that might have a cage clamp type of connector on them, and then additional proprietary types. Mentioned the Neo motors, the brushless DC motors that have an integrated encoder in them. There's a couple of encoders that are used in FRC pretty heavily, and they all have connectors that vary. So, and mentioned the particular wire sizes and colors are often required by the FRC robot rules, but also that complies with standards and practices from other areas.
The goal there is so that the robot inspectors can look at the robot and have an understanding of what's going on. So the rules actually specify color choice for everything, with the one caveat that if it's pre-attached, you can use it. And the rules are standard colors that comply with, established standards. So there's nothing weird going on there.
Yep. All right. Let's see. what kinds of things are we going to see with signal wiring? They're mainly sensors and communication were the two categories that I saw fit to split that into. Um, on our last robot, we used photo detectors for um, determining ball location in the robot. Um, and the photo detectors consisted of uh, a light source and a light sensor, and you mounted the two on opposite sides of where you were looking for something to be. And if the light source shot through to the detector, then there's no ball there. And if it was blocked, then you assume there's a ball there. We've used some micro switches in the past for limits, like on a excuse me, like on a lift or on a 4-bar, so that you don't overdrive that with the motor. Um, and Encoders are essentially shaft rotation sensors. Many other types available. We've got a couple of air pressure sensors that are analog, that we haven't made it through to a final robot with it yet, but I've got hope someday we're gonna get that put on the robot and functioning. Pneumatic system on the robot, we have an air compressor that creates air pressure, and then we store that air pressure at a high pressure, and then we go through a regulator to the solenoid valves, and so we use that air pressure at a lower pressure. And so by using a regulator, you can have a consistent pressure at your devices, but you can store the pressure at a higher pressure. That way you can you can have some swing in that high pressure supply. As it drops too low, the air compressor kicks on and pumps it back up, and then when it hits an upper limit, it shuts off, and you can store that air pressure at a higher level, like 120 psi, where you would use that pressure at 55 or 60 psi, or maybe lower. You may turn that pressure down if your cylinders are sized that's just too much force. But anyway, one of the ideas that we've tinkered with over the past is using an analog pressure sensor on the high pressure storage to give the robot operator a kind of a gas gauge of how much he's using his air. And likewise, if that goes flat, then he knows he doesn't have any air pressure, or she. Communication and network standards. We're using Ethernet to communicate, and there's an Ethernet mesh radio that connects to the RoboRio, and then we also had a camera that connected on Ethernet this last year. We've used USB cameras in the past. This last year we used a USB inertial measurement system, gyroscope kind of orientation and position sensing. The CAN bus is probably the the big one that we deal with a lot is that CAN bus network. But there's a lot of other types available. There's I squared C. There's other types of communications and networks available to be on the FRC robots. And so wanted to throw that out there that just because I didn't list it doesn't mean that we can't use it. There's I think I think the RoboRio even has RS-232, which is like old school serial cable kind of stuff. And wanted to mention in here the MXP board. That allows us to add custom circuits and connections to the RoboRio. We've thus far only used it for adding custom connectors. But there's a lot. We've only scratched the surface of what that MXP board can be used for, as far as installing custom circuits on the robot. Don, do you have any particular comments on the MXP board as far as what the limitations are on that? I know we can't have any energy storage on it.
Right. They primarily want you to only have passive devices on there.
Okay, but, so no Arduino chip.
No, you can't throw another processor on there. Okay. In the past, we needed to turn something on and off, like our targeting camera. And we had a power field effect transistor on there that would allow us to turn on and off 12 volts, so that if we weren't actively targeting, we could shut off our targeting LED ring to basically save power, because power is critical. But the main thing that we've used them for in the past is to get some things out. One thing we used it for is to get an I2C connector that had mechanical retention. However, my experience with that was for a gyro board, but the USB approach for that, I think, is much better, because I2C doesn't really lend itself as well to having a longer distance, and USB is designed for that. So but based on what we do for a game, we can decide what we could add for the MXP board. And the rules, in addition to the MXP board, the rules do allow custom electronics. And we can design something and put it on our own board and 3D print a case for it. And a lot of teams don't do that. And it's a point where you can basically score some points with the judges. So it's an option.
All right. So let's see. The next slide I've got here is CAN network. We've mentioned that quite a bit already. There's, but it is an SAE standard. That's Society of Automotive Engineers. Let's see, green, yellow, twisted pair, 1 full twist per 2 inches or 50 millimeters. So that's a half a twist per inch. Um, it's a daisy chain or trunk and tap style of network. It requires a 120 ohm resistor at both ends of the trunk line. There is one built into the Robo Rio and another one built into the PDP. The one at the PDP is jumper selectable. And the last few years, we've not been using that one. We've been selecting that one out and putting our own at the end of the chain. That allows us the flexibility to not have to have a complete loop. Especially like for instance, 2 years ago now we had a lift on our robot and had a couple of motor controllers for part handling on the end effector of that lift. And so instead of having to run a pair up the lift and back down, we could run one pair of wires up the lift and terminate that as the second end of the trunk. And so that was something that a lot of teams didn't do. A lot of teams didn't know you could do, or were daunted by it and didn't want to take that on. So let's see, down here at the bottom, this is cut and paste off the web for the design topology of a CAN network. So over here at the one end, you've got your terminating resistor. At the other end, you've got your other terminating resistor, and then ECU. I forget what that is. It's electronic control unit or something like that. Now the minimum DO here is the minimum is 0. And this is kind of funny to me because the standard says that the RL, that terminating resistor, shall not be located exactly which is kind of funny to me, but it works, and it's when you're
cut out for a moment.
Oh,
does it say that it can't be located within the ECU?
Yeah, according to the SAE standard.
Okay, well,
which is exactly
we're
what we did with
first,
the Robo Rio.
So we do something different. The first ECU, is the Robo Rio, and it has the resistor built in.
Yep.
And in the case of if you use the one internal to the PDP, then that's built in also.
Right. So
the minimum is 0, so that kind of means it's inside.
Yeah, doesn't it? Anyhow,
anyway, we're fine.
So that's 100 millimeters, 4 inches, a maximum of 40 meters.
Yeah, if our robot's 40 meters long, we've got a problem.
Yeah, well, I mean, they're talking, this is an automotive standard, so they're talking about stretching a node length from the front of a semi to the back of a semi within 40 meters.
Yep.
And that's why we're using it for FRC, is because it's an automotive standard. It's very robust. It's pretty well bulletproof.
And we don't have to be that anal about the one full twist for every 2 inches.
Yeah, it's pretty forgiving.
Different spans can have different twists to them, and it actually kind of helps.
All right. Uh, anything else you want to say here, Don?
No.
All right. Um, gosh, we're coming up short on time already. Um, so, gosh, the I should have led with this. um, we talked about at the beginning the workmanship is key. Most anything that goes wrong on our robot on the field, most anything that happens is a workmanship issue, not a design issue. And the single most important idea that I can't stress enough there is the tug test. When you crimp a terminal on a wire or you shove a terminal into a connector, pull on it. And if it pulls back out, it's no good. Um, try again. Um, if you do it twice and it pulls off both times, then get some help because you're doing something wrong. Um, a good crimp on a terminal starts with matching the size of the terminal, the size of the wire, and the correct tool. There's so many times I've seen that happen that, well, hey, I've got this ratcheting crimper for pre-insulated terminals, and I've got the wrong size of wire or the wrong size of terminal or the terminal that doesn't match up with the tool they're using, and it just doesn't work. It's nothing wrong with the tool, nothing wrong with the terminal, nothing wrong with the wire, except that they don't match up.
The other thing is if you're using a connect a tool or you're doing something you've never done before, it's probably a good idea to get a mentor and work through that for the first time so that you're not just winging it.
Yep. So I'm a big fan of spot soldering. I that here's an example of that right here, where you crimp your terminal on the wire, and you come in with a soldering iron and just put a little bit of solder on that crimp. That crimp is like a staple, and so there's by putting just a little bit of solder on there, you can metallurgically bond the wire to the terminal, and that'll do a great job of connecting of getting a good connection, a good low resistance connection.
And if you've never soldered, we can teach you. Soldering is a little bit of a skill, a little bit of an art, and we can definitely teach you how to solder.
Yep. Now, solder does occupy some physical space, and sometimes we don't have room for that in a small connector hood or something, or if you get a little sloppy about it, a big ball of solder on there. This is really nice here, but if you get a little sloppy about it, have a big ball of solder on there, it can get in the way of inserting those into a connector hood. So the next thing was strip length on your wire going into the crimp. So each of these connectors I'm showing on this screen here have both a wire crimp and an insulation crimp. Not all terminals have that insulation crimp. That's there for strain relief. But I love this connector. I love this picture right here. because I think this is just exactly right. That you see a little bit of copper behind the crimp, you see a little bit of copper in front of the crimp, but not excessive. Um, this one's pretty good, but I would say that that insulation is all the way up against the back of the wire crimp, and I don't like that. You don't know that you don't know that there's no insulation in that wire crimp. Here, you're sure. Um, Again, here, um, you got a little bit too much strands coming out of the end. Um, and likewise, it looks like they didn't place their crimp die in exactly the right spot, because you got the back end of this that's not crimped. But I like
We lost you.
that. Um, where someone has taken a good crimp and sawed it in half, and you can see there the way the way the strands of wire deform, and they all started round, but look at this triangle here. I mean, it's pressed to fill the space. And then that also indicates that where you go and you solder and you fill in all those little gaps. And so that's why I wanted to include that image in there. So, Don, have you got anything you'd like to add?
The biggest problem that I've seen is the wire being too long, stripped too much, and it's just something that with practice you'll learn how to do.
Yep.
You don't want your strands of wire to be going past the crimp and into the business end of the connector.
Yeah, this is a good example of that. That those little end strands will kind of go every which way and can get in the way if you're shoving that terminal into a housing.
Right. For the Molex connectors, we shove it into a plastic housing, and if there's too much there, it won't fit.
Yep. All right. Okay. So, clean wiring as far as wire management. Especially on a robot where we're going to be running into other robots, we're going to be bouncing into walls and field components. We want to have things. We want to have our wiring tied down well. I like to see a conscious amount of slack at termination points. A lot of times this here is called a service loop. What that does is it's a planned amount of slack there that should that termination get broken sometime, you can cut these tie wraps and you've got extra wire there to re-terminate and re-land it. That's a bit excessive. Just a loop is fine. It doesn't have to be a full 360 there. But also we want to focus on making sure wires get labeled in the future. That is a huge help to troubleshooting, where you have matching labels on both ends of every wire. Make sure that when we mount things to the robot, we mount our wire bundles to the robot, that we need to have a planned amount of slack at moving parts, so that as an arm lifts up, that there's an adequate amount of slack there, that you're not pulling on it. We want to have those wire bundles rigidly tied down. Smooth combed out wire bundles is just kind of a neatness kind of thing. And then confine the wiring so that it doesn't get snagged on things. And zip ties, spiral wrap, drag chain. I threw braided motor leads in here because that was something that one of our Purdue student mentors was excited about, when we had 3 lead motors with the brushless motors. Well, we should braid those together, and all right, well, I don't think that really, he was talking about electromagnetic interference, and the same way you twist a pair of wires for a network connection to reduce electromagnetic interference. He was wanting to braid the motor leads together. The motor leads are 6 inches long. I don't think it's really that big of an issue.
It does make it look neater, and it is a good concept. And that's also why the red black zip wire is good.
Yep. So
it ties them together.
Absolutely. Hurt anything. More as a EMF. I know what.
You're cutting out.
Also, there's some spiral down here in the bottom here. These are industrial things, so it's not gonna go along with our robot totally, but these are some robots. So you've got well, there's some discussion points here. There's gosh, these are pulled awfully tight. Can you guys see my cursor? Or?
Yeah.
Okay. So yeah, those are pulled awfully tight. I'm not a big fan of that. Where these are all looped down to a point underneath there that they're tied down, and I like that better. The spiral wrap well, they tried. I would really like to see the CAN bus and the power for the Rio tied down to that back panel, rather than just kind of skying across there.
The other thing that does is with the long loopy CAN bus in that right picture, as the robot moves, it's going to flex a lot. And that's going to want to pull those connections out. So if you do tie it down, so you've got a small loop and you've got a tie wrap somewhere close to where it ties to the board, then you don't have to worry about it coming apart so much.
Yeah, yeah. I would love to see a loop in that wire right there. Back to that, they've got this all mounted on a clear plexiglass,
Right.
tie wrapped down to that board right there.
Yep.
A nice loop that gives it some slack, but then you're taking the entire weight of the wire to the board instead of to the termination point.
Right.
And so these were some random robot pictures I found on the internet. But these are on our robot. And so we've got work to do. There's some things here that are okay. And there's some things here that need some work. And so just want to throw that out there that I like to think of these things as a continuous improvement, sort of a let's see, old arrow.
Would your page up work or page?
Maybe. Hey, it does. How about that? All right. So let's see. Another thing I like to see is when we plug things together, especially with those Anderson connectors, I like to throw a tie wrap around that to keep it secure. One of the other things that has been a concern of mine in the past is we often don't plan where to put the battery until the last minute. The battery is a pretty significant amount of weight. If kind of a pet peeve of mine is that we should plan where we put that sooner rather than later and in the design process. Yeah, let's move on here. Oh shoot, we're at time. On our team, we do lump pneumatics in with electrical. A lot of the concepts are the same. That you're connecting point to point, and one of the things that I like to say about the pneumatic system is that it is not a required system. We've had robots in the past without a pneumatic system. It is a really handy system for linear motion, using an air cylinder. But it's kind of one of those things that if you're in for a dime, you're in for a dollar. There's a lot of components involved in that pneumatic system, and it weighs quite a bit. So you probably don't want to put a whole pneumatic system in for one cylinder. So
yeah, the picture shows it pretty well. That one cylinder in the bottom is what's giving us what we want for motion. And then all the rest of the stuff in that picture is overhead stuff that you have to add to get that one piston to work. So you need to have, if you had another piston, then you don't have the extra overhead stuff, but it's not simple.
Right. And so this comes in at the beginning of the design process, I think. That you want to kind of look at the robot as a whole, and if you absolutely need a pneumatic system for this one thing, then you probably want to use it on some other things also to get the most benefit out of it. And a lot of these things are the compressor itself is a motor, and I'd love to see a compressor with a brushless DC motor. That'd be cool. To take advantage of the weight savings. But there's a pressure switch and a pressure relief valve. The storage vessel and the dump valve, and you got a pressure gauge on your high pressure side. You've got a regulator and a gauge on your low pressure side, and then a solenoid and cylinder for each of the devices that you're operating.
But there's more. When you do it, design that into your robot, the rules say that those gauges that he just mentioned have to be visible easily from the outside. And the other thing is that you can't do it the way it's shown in that picture. Everything needs to be tied down. And that's also problematic. So, that what's shown in the picture would work if you had it sitting on a table, but it's not adequate for a robot. And the other thing is, if you do add a whole bunch more cylinders, you're going to find that you don't have enough compressed air to run them all. So I've seen robots with 6 air tanks on them. That's more weight.
Yeah. Yeah.
So anyway,
the minimum pneumatic system, and like you said, if it's going to sit on a table, on the robot, it's there's some details missing.
Yeah.
All right. All right. There has been there have been posts on the FRC blog and Chief and FRC subreddit and all kinds of places about the 2022 control system update that looks now like it may be 2023. There's a RoboRio 2.0 that they are saying is incremental improvements. So more memory, faster processor, better low voltage protection. I'm not sure what that means, because I mean we have it brown out now. Maybe that, I don't know, maybe they're going from a 5 volt to a 3 volt system.
One problem with the existing RoboRio is if you short one of the red wires to ground, that entire banks of I/O get killed. So it may be that.
Okay. Yeah. They are talking about a faster processor, but it sounds like no GPU, which on Reddit anyway is seems to be a popular thing to complain about. That if you plug a USB camera into your RoboRio, it's really not well suited to handle video. And it doesn't sound like that's going to get any better. The new PDP, all 20 channels will be 40 amp capable now. where only six were before.
I think it was 8. I think it's 8 and
Was it
8.
eight? Okay. I do know that. Yeah, I think you're right. I think it was eight because we did a six motor drivetrain and a three motor climber and had to move one of them off to a lower current one year.
The
Uh,
software switchable channels will be really nice because then you could plug a light ring into there
yeah,
and be able to turn on and off via CAN.
that's exactly what I was thinking of there was that um I don't know that I initially I was thinking a motor circuit and couldn't quite figure out how that would be useful, but to versus having a motor controller. But yeah, you hit the nail on the head. A ring light for your camera, or we did a shooter and a uh, um, just an LED an LED flashlight with a focusing lens to put a spotlight where we were shooting at one year, and we got a little bit of pushback from some referees who thought that we were trying to blind the people in the driver's station with our spotlight, um, and thought that we should shut that light off. This would be a perfect example of where that would be useful. Um, they're talking about a new voltage regulator hub. I'm not sure what they mean by hub. It may just be language to differentiate it from the voltage regulator module that's currently part of the system,
I'm hoping it has more outputs.
or maybe something stackable. I don't know. That it would have some expansion capability. I don't know. Likewise, they're also talking about the new pneumatic hub. Um, and one of the things there that I think is really neat is support for analog pressure feedback. Um, and 12 solenoid outputs versus 8 on the old one. Um, so lots of neat stuff there. I editorialized here a little bit. Um, that's a lot of power consumption, and we can run a battery flat in a match now. So I don't know. Maybe we'll look for changes to the battery rules to come sometime following. I don't know.
I
Uh,
don't know. It's
but
it is it's going to make things harder if we have more options.
more options makes things harder. Yeah, yeah, it does, doesn't it? Also, there was rumors of a new mesh radio that was going to follow the control system upgrade. I don't know if that's going to catch up with it in 23
I
or
don't think
sometime
so. I
later.
don't hold your breath on that one. They seem to think that they have the radio solved, even though it's a terrible product. Those mesh radios are sensitive to vibration. They can be broken.
Yeah, which we've been mounting ours on shock mounts for years. And so when people were talking about the 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 radios couldn't take shock, and so we were kind of like, yeah, we know.
Yeah, they're consumer electronics. They're made with lead-free solder, and lead-free solder is more brittle.
Okay, yeah, and so the G-force loading of shock loading and vibration, just being on a moving vehicle like that, Um, and that's all I've got. I had some discussion points here for if we ran short, but we didn't run short. But I always like to stress continuous improvement. Every season, competition, and match. Let's get out there and try to do better than last time. And good, thoughtful questions is key to that. Being observant, not just an inspired idea, but also being able to, also catching the, hold on, that doesn't look right. And identifying those problems before it leaves us dead on the field. Striving for excellence, that goes back to workmanship and no shortcuts or hack jobs. The way that happens is we're prototyping something, and a lot of times those, oh, let's just slap this together really quick to get a prototype working. A lot of times that'll find its way onto the final robot, and we need to be mindful of that. Not to say that we can't rapid prototype, but we need to make sure that those things get cleaned up and finished before they make it to the final bot. And of course we've got to be safe. We've got to take care of ourselves. Yeah, this was your line, Don. Respect your tools. Mind your fingers and eyes. The tools are tools for a reason. They leverage our capabilities, whether that be through leveraging force or cutting surfaces, and
or heat.
Or heat. Yes, I wasn't even thinking about soldering, or heat guns, or whatever. So, and mind your fingers and eyes. I was thinking cutting tools there again, and a lot of times a cutting tool will send a fragment flying off across the room. So
well, diagonal cutters can make little wire fragments fly too. We need to be wearing our safety glasses.
Absolutely. Okay. So I'm not looking at the chat. Is there anything in there that we need to?
Nothing's popped up for a while.
Okay.
You're all good.
All right. Well, let's go ahead and close out the meeting then, and do it again next time.
Okay. Thank you so much. You guys have a good day.
Thanks, Eric.
Bye.